second day. Today we are very pleased to have Vincent from the US giving a talk on second-order asymptotic information theory. Vincent did his degree in State University, then did his PhD from MIT. He is in the EC and Math department at the US. His research mainly focused on second-order and third-order these days on of various problems in single and multiple simulation theory, and uses techniques from information spectrum. Hopefully, he teaches what he's using.
So thank you very much, Chandra. Thank you very much also to Sid, who is not here, for inviting me. It's a great pleasure to be here. 5 years ago, I was at the North American School of Information Theory in California, and well, now I'm here, hopefully sharing my experiences on information theory with you. So today we are going to look at information theory from a slightly different perspective from what you are used to in, say, Culver and Thomas. And by the way, a prerequisite for trying to understand the material here is a good course in basic information theory at the level of Culver and Thomas. So that's what I will assume. I will assume that you know what are the basic measures information such as entropy, mutual information, and so on. And I will also expect that you know the basic coding theorems like the source coding theorem and the channel coding theorem. If you have some exposure to network information theory, that would be good, all right? But that is not really required. So as I mentioned today, we will look at information theory from a slightly different perspective from what you're used to. In particular, in information theory, you are taught to prove coding theorems for which the probability of error or the probability of excess distortion tends to 0 as the size of the as the block length grows. Okay, as the number of realizations of the channel or the source grows. Here we will look at information theory from the lens of the error probability being non-vanishing. That is, it is upper bounded by some epsilon, which is a number between 0 and 1, strictly between 0 and 1. Okay, then what can we say about the achievable rates? What can we say about the set of achievable rates in a network setting, right? So now we have relaxed the condition that the error probability vanishes, and we want to look at the achievable rates, okay? So that will be the focus of the talk, and we will focus on a bunch of different problems, both single user and multi-user, okay? Depending on how fast we go, okay? And feel free to stop me anytime. All right, so this is the outline of the talk. There are many topics. I'm not sure whether I can cover everything, but I really want to get through 1, 2, 3, and 4, okay? And I will do 2, 3, and 4 on the board. The rest I will do using slides, okay? So first we will talk a little bit about what I have already said. So, okay, I'll give some motivation background of information theory. And then we will proceed to a very important topic, which is binary hypothesis testing. We will see that if we understand binary hypothesis testing and the asymptotic expansions therein, fixed length lossless source coding, fixed to fixed length lossless source coding, and channel coding can be done quite easily. Next, we will talk about channels with state, okay? State both at the encoder and at the decoder, as well as a decoder only. For state only at the encoder, there's a problem where this is not solved in the second order sense. Next, we will talk about Slepin-Wolf coding as well as some simple classes of Gaussian interference channels. Very simple ones, okay? For which we know the exact second order asymptotics. Okay, so let me just go ahead and please, as I mentioned, feel free to interrupt at any time. Okay, so that's the agenda. I have 4 hours. We can take our time. All right. So, oh, there's one more topic. I'll talk a little bit about open problems towards the end. Okay, so let us go back to information theory. Okay, information theory started off with a bang in 1948. This gentleman. And this is Shannon's figure 1, in which, well, he proposed the architecture for a communication system. First, there is an information source. Then we encode it somehow. And there is some noise from the channel. And the output from the channel is then received at the decoder. And we would like to then decode the message, which can be a memberless source, video, an image, etc. Okay, so the study of information theory is really to find the fundamental limits for reliable communication, for reliable transmission or compression. Okay, so in particular, to motivate my talk, I will talk about channel coding. all right? And this is a topic that we will revisit in great detail later on, okay? And in my talk, I will try to do proofs, okay? I'll try to do very simple proofs of things that, of some theorems, so that you get some sense of where the results come about and how the results come about, okay? Right, so in channel coding, there are a few different aspects, okay? So we have something called a message set, right? Which is, you can think of as a bunch of numbers, okay? An encoder, F, and a decoder, phi, okay? So here, different from channel coding setups that you have seen, we are only using the channel once, all right? So this is called a one-shot setting. In usual channel coding, for example, in chapter 7 of Cover and Thomas, we use the channel multiple times. But you can think of using a channel multiple times as using a super channel one time, right? So we can always replace channels that are used multiple times with a single W, right? That maps super letters to super letters. So this is without too much loss of generality. In fact, it's very general, okay? So we can then define the average error probability as the probability that the decoded message is not the same as the true one, okay? This is all very standard. Here, M is uniform on the message set. And what are we concerned about in information theory? We are concerned in channel coding, in particular, with this quantity here, okay? Which is a non-asymptotic fundamental limit for channel coding. And let's try to parse what this is, okay? It is the maximum number of messages, okay? The maximum number of messages, M, for which there exists a code with that number of messages, and the probability of error, the average probability of error, not exceeding epsilon. So this quantity here is parameterized by both W, the channel. Of course, the number of messages you can transmit over a channel depends on the channel. And it also depends on the tolerable error probability epsilon. Okay, if you can tolerate an error probability of 99%, of course, you can do better than a probability of 0.01, of course, right? So a central problem in information theory is to characterize this quantity here for different classes of channels, for channels that are used multiple times for different values of epsilon. Okay, so this represents the maximum number of messages you can transmit over W with average error probability epsilon. Okay, now if you take the logarithm of this quantity, it's the maximum number of bits, if the logarithm is measured according to base 2. Okay, so as I mentioned, this setup is the so-called one-shot setup. We can consider using a channel multiple times. Nothing changes, okay? So, for example, if the channel is a discrete memberless channel, the input alphabet is finite, the output alphabet is finite, and we use the channel multiple times, okay? We just simply replace the input word, the input symbol by xn, and the output symbol by yn. And if we use the channel multiple times, I will use the notation W superscript, which basically means that it transforms a sequence of input letters and symbols into and output symbols in this memoryless and stationary fashion. Okay, so what are we after? By using the notation that we derived, that we stated on the previous slide, it is not too difficult to simply replace W superscript n. And this is what we seek. So this notation is very convenient for us to insert various channels and various epsilons. All right. So what we seek is this, but this is usually computationally difficult because we have to search over all possible codes means all possible encoders and decoders, and this is too easy. And so what we want is to approximate this, and in particular approximate the logarithm, which is the maximum number of bits we can transmit over n users of the channel with average error probability not exceeding 1. Okay, so what do we know? Okay, so I will be talking in the maybe fourth part of my talk about how we can derive such a result. But this is just to give you some flavor of what we are going to do. So for every fixed epsilon, so that's the number in between 0 and 1, and for most well-behaved discrete memberless channels, we can expand the logarithm of the maximum number of code words we can transmit over n users of a discrete memberless channel as follows. So the first order term is capacity, is a linear term multiplied by capacity. The second order term is scales with square root of n, and the constants are also well defined. And the third order term is usually something that is quite difficult to derive, but I've just stated here. So this expansion holds for most well-behaved discrete memberless channels, and it's due to these people. Okay, so this work was this line of work was I mean the most prominent work in the early days of information theory was pioneered by Strassen. And this line of work of fixed error probability asymptotics was revisited recently by Masahito Hayashi, among others, Polyansky, Verdú, as well as myself and Otoma Mitchell. Okay, so let us now try to understand what this means. Okay, let us drop the third order term. So the maximum rate, the maximum number of bits we can transmit per channel use is the logarithm of the maximum messages divided by n, divided by the block length, okay? And if we divide the previous expression by n, we see that this is exactly what we get, okay? Dropping all the remainder terms. So, well, what does it say? Well, the interpretation is that the backoff from capacity at some finite block length n and tolerable error probability epsilon is approximately that quantity, okay? You reverse the sign here, you get phi inverse 1 minus epsilon, which is square root of V over n Q inverse epsilon. So this quantity for epsilon less than half is positive, and thus a small error probability implies a large backoff. So we can actually compare this to finite block length bounds, and this was done in the very nice work by Polyansky, and Verdú. And what they show is that the Gaussian approximation is for some n and some epsilon of practical interest. Okay, so this is what we will derive in the later part of the talk, just to give you some sense of all these means. So here is a BSC. Here's the performance plot for a BSC, and the BSC has probability conveniently chosen to be 0.11. Okay, and so the capacity is 0.5 or half bits per channel use. All right, so if we fix the error probability, average error probability to be 0.1, say 10%, and we use a block length of about 500, that is the maximum rate we can obtain, approximate maximum rate we can obtain by using the normal approximation. So there is a gap between what we can attain and the asymptotic fundamental limit, which is capacity. Okay, and you can play around with this plot, and you can change the error probability. Okay, you can change the error probability, you can change the channel parameters. I'm not going to do that. But for the purposes of today's talk, we will focus on not actually computing the finite block length bounds, but actually computing the second order expansions. How do we get such remainder terms? Okay, so that will be the focus. And we will look at problems involving binary hypothesis testing, source coding, channel coding for point-to-point problems, and then move on to more sophisticated systems. All right, so let us go back in time to the beginning of information theory to further understand this quantity. Okay, so Shannon's coding theorem and the strong converse by Wolfowitz shows something. Okay, shows the following. Okay, that if you fix an error probability epsilon and you use the channel n times, the maximum number of code words you can transmit, I denote by m star wn epsilon. Okay, so that's the maximum number of code words you can epsilon reliably transmit across n users of a DMC. And you take a logarithm, that's the maximum number of bits. You divide that by n, you get the maximum the number of bits you can transmit per channel use. You fix any epsilon between 0 and 1, and you consider that quantity. Somewhat surprisingly, at least to someone who doesn't know information theory, this limit exists, and it equals to a number. The number is called capacity. Okay, the capacity is defined as follows, and we will use the notation IPW to denote mutual information. So as most of you should know, mutual information is a function of the joint distribution. It is a function of the input distribution and the channel. So we will make that explicit. Okay. Oftentimes you see IXY, IX semicolon Y, but I'm not a big fan of that notation. I prefer to make the distributions explicit. So mutual information depends on P, the input distribution that we can optimize over, and W, which is the DMC that we are given. Okay, that we cannot. So this means that we transmit most of the time at positive rates, which was quite surprising in the 1940s. 1950s. So great. So that is the first type of asymptotic expansion for log m star. And so here are some remarks. The channel coding theorem, most of the time, is in fact for DMCs independent of epsilon. Okay. So what sort of plot can we do? So here is the asymptotic optimum error probability as a function of the rate. Okay. And there is this special point here, C, capacity. So how does this look? Now, for all rates below capacity, we know that there exists a sequence of codes of rates less than or equal to less than capacity, and the error probability can vanish. So that means that in this part of the plot, I have 0. Now, perhaps what is not so well known after you have only taken a first course in information theory is that if you transmit at rates above capacity, the error probability goes to 1. This is called the strong converse. Okay, and it can be proved through many different ways for DMC. So this plot looks as follows. And really, we do not know, at least at this point, it is not clear what happens at capacity. All right. To indicate I do not want to discuss what's happening at capacity. And typically in the first course on information theory, we don't discuss what's happening at capacity. Okay?
Speeding in and out and the recording may, sorry.
Okay, thanks. So that's the plot. And so there's what people call a phase transition between what is possible and what is absolutely impossible. So today, we want to examine what happens at capacity, right? So what happens at capacity? More precisely, what happens if the total number of messages, which is this cardinality of the message set, scales at n multiplied by the channel capacity plus some constant multiplied by square root of n. Now, observe that if I normalize both sides by n and take the limit, I recover capacity. So really, we are operating at capacity, okay? But we have a back off or an additional term of L square root of n. So what happens? Here, L is known as the second order coding rate, and this goes back to Hayashi in 2008 and 2009. Okay, note that L can be negative, even though it's called a rate. So this term has stuck. It is probably not the best term, but it has stuck. Even though it's known as a rate, it can be negative. So if L is negative, it means we are backing off from capacity. If L is positive, it means that we are using a code that at finite block length has a rate higher than capacity. Okay, so we can now look at the optimum error probability of a block code, okay, as a function of L, with the capacity being fixed. And we can ask the question, what is this optimum error probability? So, as I mentioned, if we normalize both sides by n, then the rate satisfies expansion here. And we can then look at the previous plot as a function of the second order coding rate L, okay, because we have fixed the capacity. Okay, so now as L becomes really small, it means that we have fewer messages, right? So we expect that the error probability is smaller than if L is larger. So this plot should be monotonically increasing at the very least, right? So it turns out, and this is what we are going to prove, and this is not so trivial, that the shape of this plot is a Gaussian, okay? And there are some constants here that involve, of course, the second order coding rate L, and a term that is known as the dispersion of the channel. And this term dispersion goes back to Polyansky, Poe, and Perdue. So we can ask a slightly different question. For a fixed error probability epsilon, okay, so we look at a horizontal line here. For a fixed error probability epsilon, what is the largest second order coding rate that I can achieve? Okay, that represents, in fact, the maximum number, that is roughly an approximation to the maximum number of messages that I can transmit above capacity. roughly speaking. So now if I set this to be epsilon, if I set this entire quantity to be epsilon, forget about O1, and I solve the equation, this P can always be inverted. If epsilon is between 0 and 1, then I observe that the largest L star is in fact square root of V, phi inverse epsilon. And that really explains the second order term in the asymptotic expansion. Okay? So this is yet another perspective of looking at second order asymptotics from the viewpoint of the optimum error probability. So here, the rate of the code, I want to reiterate that the rate of the code is C plus a term, which can be positive or negative because L can be positive or negative. All right? And depending on whether L is positive or negative, we get some non-zero error probability, as you can see here. All right? It's never, 0 never going to be 1. And the larger L is, the larger the optimum error probability because we have more messages that we want to transmit. All right? So this curve is very natural. The shape of the curve, that of it being a Gaussian, requires a proof. And that is something that we will try to convince of. At least I will show you the main proof techniques in this tutorial. Okay. So I just want to mention other quick, okay, before we transition to the board. Some of you might be familiar with error exponent analysis, okay? And in error exponent analysis, we do something that is dual to what we are doing in this talk. So in error exponent analysis, we typically fix a rate, R. It is either above capacity or most of the time below capacity. And we ask the question, what is the optimum error probability? Now, if you fix the rate below capacity, then it is obvious that the error probability can tend to 0 by Shannon's. However, what is not so obvious, it tends to 0 exponentially fast. And it does. And this function, as a function of the rate, we call the reliability function or the error exponent, depending on the book you read. And most of the time, the error probability decays to 0 exponentially fast with an exponent that is the error exponent. Okay? So here we fix the rate and we ask for the optimum error probability. Okay? But in today, we instead fix the error probability to some number strictly between 0 and 1. And we ask for maximum number of messages that we can transmit. Okay? Or we ask for the back-off term from capacity, which is this L business that you saw in the previous slides. Okay. So, channel coding, there are three quantities that we are interested in. Number one, we're interested in the rate of the code. We want the rate to be as large as possible. Number two, we are interested in the error probability. We want the error probability to be as small as possible. Number three is the length of the code, the block length. Okay? In both these analyses, the block length goes to infinity. The block length goes to infinity. But what is different is the object we are fixing. In error exponent analysis, we are fixing the rate. It is a number strictly between or strictly above. Right? And we ask for the optimum error probability. In normal approximations or second order analysis, we fix the error probability to be some number that for the maximum number of messages or the back-off term. Okay, so the agenda for today's tutorial I have already briefly sketched, and now I will talk a little bit more about it. Okay, so we will talk about point-to-point communication first, and we'll try to understand. And really, the first part of this talk here is, I would say, a tutorial on Strassen's paper. Strassen wrote a paper in 1962 in German. It is kind of hard to parse the difference in the notation. So in the first part of the talk, I will try to explain the various parts of Strassen's paper in modern language. So in particular, Strassen's paper, for channel coding, the Y is the input and X is the output, so it's a bit hard to parse. So these are the topics that we will discuss, very important point-to-point topics, okay? And then we will talk about more modern stuff that myself and my collaborators have worked on, including channels with random state, with coding, as well as simple Gaussian interference channels. Ones. Any other topics that we can talk about? Try to keep things to to the bare minimum, so that you can appreciate the topics and you can explore further if you wish, and you can explore further by reading my book, my monograph. There are several other topics in there that I have not discussed, but if you can understand 50% of what I'm talking about, that would be a very good starting point to reading the topics in my monograph. Okay? Great. Can we transition to board now? Thanks. So now I want to talk a little bit about binary hypothesis testing and asymptotic expansions there. It turns out that binary hypothesis testing is fundamental in allowing us to understand the fundamental performance limits of source coding and channel coding. All right. If we understand binary hypothesis testing properly, then source coding and channel coding, at least fixed length source coding and channel coding, will be a breeze. Okay. So what is binary hypothesis testing?
Could I request the audience to come sit in front? It will make it easier for you to see.
Yeah, I mean, if you sit in front, it will make it easier for you to see. But I will try my very best to write as large as possible. Binary hypothesis testing. So this is a topic in estimation and detection theory. And as I mentioned, it is fundamental for us to understand this before we go further into lossless source coding and channel coding. So what is binary hypothesis testing? The simple case. I don't need that for the moment. Yes. So that can be pushed to the side. Okay. So in binary hypothesis testing, we have two hypotheses, which we typically call the null hypothesis and the alternative hypothesis. Okay. So in the null hypothesis, there is a random variable, but we do not know what its distribution is. Okay. So in the null hypothesis, the random variable is distributed as P, and in the alternative hypothesis, the random variable is distributed as Q. So P and Q are assumed to be different, of course, otherwise things get very boring. Okay, so the hypotheses that are different. So this could model a scenario where the null hypothesis is that of a signal observed without noise. A signal observed without like a DC phase, the DC component, or say a signal observed without an airplane in the sky. Whereas in the alternative hypothesis, there is an airplane in the sky plus some noise. Okay. All right, so those are the two distinct distributions. And here, these distributions, P and Q, are assumed to be different, okay? And they live